Today we're going to take a look at section 3.3, increasing, decreasing functions, and the first derivative test. Okay, this is they're all related together, these ideas. All right, so to start talking about, we're going to talk about what we mean by increasing and decreasing. So an increasing function is one where if x1 is less than x2, then f of x1 is less than f of x2. Okay, I'll draw a picture here in a second. And a decreasing function is when x1 is less than x2, f of x1 is greater than f of x2.
So should that be x1 is greater than x2?
Nope, it's written correctly. Yeah, and a picture will show that for you in just a second, Hannah. Okay, so jot those intervals in there, and we're going to draw a graph right next to them. Make x1 less than x2, so x1 will come first, x2 will come second. Okay, so this image will be the same for both pictures, right? All right, and then what we want, if it's increasing, is we want the y value for x1 to be smaller than the y value for x2. So it would look something like this. And then in some fashion or another, those 2 points are connected. Okay? That's what we mean by increasing. We always read graphs from left to right, just like English is written. We read it from left to right. We read numbers from left to right, so we read graphs from left to right. So it's increasing, it's going uphill if it moves from left to right, like this. Now, we have the same picture below to start with, but the difference is that the x1 location for the y value is actually larger than the location for the x value. So we have this point, say, up here, and then this one would be maybe down here. So, right, f of x1 is actually greater than f of x2, and in some fashion or another, these two are, whoops, that didn't connect at all, did it? How about that? They're connected. Okay, that makes sense, right? What we want to do is we want to relate this idea back into derivatives when we were doing the first derivative test. So one little piece before we get to the first derivative test that's helpful, theorem 3.5, says suppose that f is continuous on the interval I. Okay, I think, yeah, it's not written here, but this I is the interval AB. Okay, so it's continuous on this interval from A to B. If the derivative is greater than 0, remember derivative means slope, so if the slope is positive, then the graph is increasing. That's what a positive slope means, right? Yeah, I mean, like, think about it. Think about a line with positive slope. Is it not increasing from left to right? Certainly. Okay? Same is true for any other curve. Doesn't have to be a line. Now, if the derivative is negative, right, f prime is less than 0, that means that the slope is negative. What does a negative slope look like? Well, you're going downhill. It's decreasing. Okay? And then if you have a place where the derivative is 0 on an extended interval, right, it means the slope is 0, then you've got a horizontal line, right? It's constant. If you just have one point where it's constant, that it may be an increasing, or I'm sorry, it may be a maximum or minimum point. We did that back in section 3.1. But if you've got an interval over which it's doing it, then it's constant. Okay? You know everything in this table, right? This chart. We've already talked about it. It's just sort of put together in a nice fashion, compiled all together for you. And we need it for theorem 3.6. Okay, theorem 3.6 is our first derivative test. So I'm going to let you fill in all the gaps, and then we'll talk through what they all mean. Suppose that f is continuous, I told you, on the interval AB, and C is a number between A and B. It's a critical number. Okay, so fill in those gaps. The first one says that if the derivative goes from positive to negative, then the graph would be going from increasing to decreasing, and we have a local maximum. The second one says if the derivative goes from negative to positive, then the graph goes from decreasing to increasing. We have a minimum. And the last one says if the sign doesn't change, you don't have a max or min. And you should have space to the right-hand side on your notes for you to draw a picture of each one of these. Somehow when I created this, I didn't leave myself a lot of space. I'll try to cram it in there. But the first one says, if it's going from increasing to decreasing, well, increasing looks like that, right? And decreasing looks like that. So can you see why it should have a maximum? Right there. Does that make sense? Go from increasing to decreasing, you have a maximum. The second one says that if it goes from decreasing to increasing, you should have a minimum. Right? Well, of course. Visually, we got that. The third one, I'll draw you a picture of what would happen or could happen. It says if the sign doesn't change, nothing's happening. So maybe you do have a location. It says that C is supposed to be a critical point, which means the slope's 0. So you have a location where it levels off and then it continues going in the same direction it already was going. Right? So this point right here is a critical point. I have a horizontal tangent line, slope is 0, all that good stuff. But it's increasing before it and it's increasing after it. And we've seen this particular graph before. It's the graph of something like y = x cubed. So the first derivative allows us to find where graphs are increasing, decreasing. That was the last one, theorem 3.5. And now it tells us we also have a way to use that first derivative to find where we would have a graph that has a maximum and minimum value for the graph. And it's worth noting that this is using the word local, right? Some other books will use the word relative. Doesn't really matter. Either one means the same thing. It just means sort of in a close neighborhood, right? When you compare just a small area of the graph. Doesn't mean on the entire graph. There may be a location somewhere else where it's bigger or smaller than that particular point, but in a neighborhood, in a small area around it, it is the biggest or the smallest value. Okay? So this is like my mom thinking that I'm tall. Some of you have stood up next to me before. Just for clarification and for the purpose of the video, I am 5 foot, maybe 4. I think I'm shrinking. So I might be 5'3" these days. Okay? Just so you know. My mother thinks that I'm tall because in a relative, for a woman anyway, in a relative area, that is my family, I'm the tallest woman in my family. Yeah, for real. In my husband's family, I'm the shortest woman. For real. Okay? So it's all, what we would say, it's all relative, right? It's the same thing here. It's this small, sort of small located area. So the first thing we're going to do is we're going to talk about just identifying the increasing, decreasing. That's theorem 3.5 kind of stuff. And then we're going to add on the local max min, which is just sort of one extra step when we go to examples 3 and 4. So our equation looks like y equals x plus 4 over x. First thing to do is to rewrite this differently. How would you rewrite it to make it more accessible for doing derivatives? To the negative 1. Right. Good. Okay. So go ahead and take a derivative of this. I will too. Is that what yours looks like? Yeah? And then it will be helpful for us to go ahead and put that x back in the denominator. It'll be easier to work with. And our goal on both of these has to do with finding these locations where we have a critical number. You see where that says critical number? Critical number. Do you remember what critical numbers are? It's been a little while since we talked about them. Where the derivative is equal to 0, or maybe where it doesn't exist, right? So for this case, if this is equal to 0, where would this equal 0? Well, we'll solve that. Where would it be does not exist? At x equals 0, because we've got a 0 in the denominator. So we're going to need, this is one of our critical points to consider, right? Not really a critical point, but a place where we might change the, make that a little bit smaller, where we might change from increasing to decreasing. So this is one of our points. The other one is going to come from, or the other one or ones is going to come from the other equation we haven't solved yet. So if you'd like, you can move these to separate sides of the equations. You can cross multiply and solve. You can multiply everything by x squared. You can do that and factor. Our goal, though, is to solve this equation. So how would you like for me to solve the equation? What do you want to do? Cross multiply. Okay, so Evan says we're going to do something like this. Move it to different sides of the equation, right? And then if I cross multiply, I have x squared equals 4. Yep, and then I would square root to solve for x. So what does x equal? Careful. Ah, positive or negative 2, so be careful with that. You square root, make sure you put the plus or minus on there. Okay, so what do we do now? Well, what we do now is we set up a number line. And our number line will include all of the critical points that we have found. So we need a number line that has the number -2, 0, and 2 on it. Now, I really don't care what happens specifically at -2, 0, and 2. I already know that. Either the derivative is 0 or it doesn't exist. What I care about is the intervals between them. Make sense? Now, here's the cool thing. Whatever is happening, say, at -4, like if the graph is increasing or decreasing, is the same thing as happening at -5 and -3 and -10 million. Because it's all in the same interval of the graph. Are you with me? So we're going to pick numbers in the intervals that we've created. And so I'm going to pick the first set. I'll let you guys pick the next one. So this would be -3 maybe, -1, 1, 3. But there's nothing special about those numbers. Generally speaking, I like to pick numbers that are easy to work with. I don't really care what the numbers are. So these are the numbers I chose. Now, I'm going to plug those numbers into something. Am I going to plug them into the original graph or into the derivative? Let's see what they would tell us. So if I plug them into the original, what kind of information will I find out? If I plug in -3 into the original graph, what will I find? The position, the y value, right? I'll find the ordered pair where I'm located. Does that tell me if the graph is increasing or decreasing? No, it doesn't. Good try. Doesn't, though. What tells me if it's increasing or decreasing? The derivative, the slope graph, right? Whatever the slope is. So I want to plug these values into the derivative. That way, if the derivative is positive, I know it's increasing. And if the derivative is negative, I know it's decreasing. Are you guys with me? So our goal is to plug these arbitrary values that we picked in these specific intervals into the derivative graph. So I'm going to plug in the values into y prime. So I'm going to write y prime of -3, y prime of -1, I want y prime of 1, and y prime of 3. These are the values I care about. And if you'll grab your calculator, you can do this very quickly. So let me show you. In your calculator, I would put this equation, the y prime equation that I just boxed in red, I'd put that into the y1 in your calculator. Okay? So just plug in 1 minus 4x to the -2. Or 1 minus 4 over x squared. Either of them is fine. Doesn't matter. And then in your table, you can plug in -3, -1, 1, and 3. You can do it very quickly. Do I care about the number answer that I get? I don't. What do I care about? The sign. So really what I want to know is, do I get a positive value or do I get a negative value? So when we plug in -3, what do we get? Positive. When you plug in -1, what do you get? Negative. When you plug in 1, what do you get? Negative. And when you plug in 3, what do you get? Positive. Okay, did everybody get those signs? That's really important. The signs are the important thing here. Now, you can use just this piece of information and go on and make your claims from here, and that's okay. But in a minute, what we're going to be doing is we're going to actually be placing those signs on our graph. So I'm going to do that here now just to remind you. So this is positive, negative, negative, positive. That's what we found right in here in these intervals. Okay? So in terms of this graph, the positive values mean the graph is doing what? Increasing. And the negative values mean the graph is doing what? Decreasing. And the directions asked us to identify the intervals where it's increasing and decreasing. So how do I do that? Well, let's start with increasing. So this graph is increasing. The first interval in which it's increasing is the one that's on the far left. How would I write that? Does this look familiar? We start with the negative infinity in parentheses. And we're always we're always increasing or decreasing on open intervals, so we use parentheses on everything. So that's kind of nice. Don't have to worry about open or close, they're always open. And there's another piece of the graph where it's also increasing, so I'll put a U for union in between. The other piece of the graph is where? 2 to infinity. Okay, is everybody good with that? Why am I using 2 and -2 and not 3 and -3? And I plugged in 3 and -3. Yeah, the 3 and -3 were what we actually call test points, right? They're just locations within the interval, but the intervals themselves are determined by the 0, the 2, and the -2 that we placed on the graph to start with. Okay, good. Now, decreasing, you might be tempted to tell me that this is decreasing from -2 to 2. If you do that, you've missed something. The asymptote. There's an asymptote in this graph, right? It is not increasing or decreasing on the asymptote. So when we write this out, we have to leave a space for that to happen. So this is -2 to 0, and then 0 to 2. So that we exclude the asymptote in the description.
Should we do a square bracket and not include 0 though?
Square brackets would include 0. We always do this on open intervals, so we never actually include endpoints at all. Okay, everybody good with that one? Okay, we're going to try another one. Because trig is so fun. This isn't just trig, it's a cosine squared. Oh my goodness. Wow. All right, process always starts the same way. If you see the phrases increasing, decreasing, you need to be thinking derivatives. Okay, so we're going to take a derivative. Cosine squared, that is a chain rule. It's a function squared. So what do I have to do to take the derivative of cosine squared? Multiply the 2 by the cosine, right, Marco? And then what? Yeah, the derivative of cosine, which is the negative of sine. That's the first piece. Now I need the derivative of the negative cosine. What would that be? It would actually be positive sine because the sign will switch. So either write down negative sine or positive sine of x. And just for the sake of cleaning up a little bit, this is -2 cosine of x sine of x plus sine of x. All right, we've got a derivative. This derivative is going to be able to tell me if I've got positive or negative values, but in order to do that, what do I need to do next? Set it equal to 0. I've got to get those intervals, right? I can't get the intervals if I don't know where the intervals are breaking apart, and they break apart at the zeros. So, please do not move things onto two sides of this equation. That's not going to help you, okay? This is kind of like when you get a quadratic equation. You have to factor. So what do they have in common? Sine of x. So we'll pull out the sine of x. That leaves me with -2 cosine of x plus 1. Now what? What was that? Yeah, good. Yeah, you're going to set each part equal to 0, so sine of x is equal to 0. And -2 cosine of x plus 1 is equal to 0. So let's start with the easy one, sine of x. The interval that we're looking at is from 0 to 2 pi. They have to give us an interval, otherwise this repeats over and over and over again, right? We have lots of repeating values with sines and cosines, so they start with an interval. Between 0 and pi, where is the sine value 0? Pi over 2. What was it? Was it pi over 2 or was it 0? It's 0. Right? The sine of 0 is 0. I think some of you are thinking about cosine. What's the other one? Pi.
But it can't be 0.
What can't be 0? That's true. That's true. We're already going to have an n value at 0. But yeah, you're correct. Actually, between 0 and 2 pi, we would only have the pi value. Yeah. We're going to already have the endpoints marked on there anyway, so it wouldn't make any difference. Over here, this would be the cosine of x equals to 1/2. Now that's a little bit harder to think about on your unit circle, so we'll see how good y'all's memory is. Where do we have a cosine value of 1/2?
This is
Pi over 3. Very good. Where else?
5.
5 pi over 3. Also correct. Well done. If you're struggling, just grab that unit circle out for remind yourself, okay? So we have actually 3 critical points, right? Because that first one doesn't really count, 0. But we do have the intervals where 0 is on there. So as I'm making my sine chart down here, I need to start at 0 and I need to end at 2 pi because I'm confined between those values anyway. I won't have like negative infinities here. I just won't. Okay? But I do have 3 values in here. I have pi over 3, 5 pi over 3, and pi over 2. Which one should come first? Pi over 3, right? That's the smallest one. What's the second one? Think unit circle. Which one comes next? Pi over 2 or 5 pi over 3? Pi over 2. And I'm not trying to sort of give you any kind of a scaling down here. I'm just placing them on here. And then the last one would be 5 pi over 3. Okay. We need values between these, correct? You can either think unit circle numbers, that's fine. You can think whole values as well. Oh, I had a pi, not a pi over 2, didn't I? I'm sorry. My bad. I'm sorry. I'm sorry. Did I fix it? Okay. Did I about give you a heart attack? Ethan's grabbing his chest like I might have. Whew. It was close. We're all good? All right. You can either use, pi over something kinds of values as we sort of use values in between these. But honestly, we're going to grab our calculator anyway. So if you wanted to use whole values or point values, like decimal point values, that would be okay as well. So if you wanted to, for instance, pi over 3 is almost the number 1. Agreed? Yeah, I mean it is. Yes? It's almost 1. It's a little bit bigger because pi is a little bit bigger than 3. So you could, for instance, use the value of 1 right here. That'd be okay. You could use pi over 4 there. You could use pi over 6 there. It doesn't matter. Pick one. Okay? Just pick one. What would you like to use between pi over 3 and pi? Pi over 2? 2? Could you use 3? You could, because 3 is slightly smaller than pi. How about between pi and 5 pi over 3? 4 should work, right? Again, if you want to use pi over something values, use those. That's fine. What could you use between 5 pi over 3 and 2 pi? 6? 6 sounds good to me. And I am not looking at my whole screen. I actually thought it was much further to the left when I was writing all of this. So let me move this. Okay, these are the values that I need to check inside of what? The original graph or the derivative? The derivative. I'm going to plug these into the derivative. So I actually want to find f prime of 1 and f prime of 2, f prime of 4, and f prime of 6. So you can take this equation, any of these equations, like this one or this one or this one, any of those are fine. Plug those in for y1 in your calculator and plug in 1, 2, 4, and 6. And what we want to know is, do we get positives or negatives? So what do we get when we plug in 1? Positive. What do you get when you plug in Did everybody get a positive on that one? I have negative written down, but I might have made a mistake. Is it negative or positive? You got negative? Okay, I think maybe negative. Double check your entry. Marco, I think you're the one who told me positive. Double check the y equals. What about at 2? Negative also? Oh, yeah, check and make sure if you're in radians or degrees. Good point. You should be in radians. Did we get positive? Okay, how about at 4? Negative? And at 6? Positive. Okay, are we good with that? Yeah, we got some oscillation. Okay. If you graph it, it actually doesn't oscillate quite like you might think it does because you've got multiplication of these going on and some squareds in there, but it is oscillating. Our goal is to write down whether these are increasing or decreasing. So over here I have negative, positive, negative, positive. Where is this graph increasing? Pi over 3 till pi. Union what? Five pi over 3 to 2 pi? Is that right? And where is it decreasing? 0 to pi over 3, right? And then again from what? Pi to 5 pi over 3. Okay, any questions on that? Okay, so that's just identifying increasing, decreasing. The next one, actually, this is a little bit even more helpful in terms of their directions. They ask us to find the critical numbers. Well, we've been doing that. How do you find critical numbers? Set derivatives equal to 0 and solve, right? They ask us to find the intervals where it's increasing, decreasing. Have we been doing that? Yeah, so parts A and B are exactly what we've already been doing. Agreed? C says to apply the first derivative test, which simply means to decide if those locations have maximum or minimum values based on whether it's increasing or decreasing on either side. And then part D says to use the graphing utility, like your calculator, to confirm. Okay? So we're going to give this a go. It's going to start out very much like the last ones. And so this one's a really clean and nice and easy one. What do we get for our derivative? Negative 4x plus 4. If you set this equal to 0 and solve, what do you get? Negative or positive? Okay, good. Positive 1. X equals 1. Everybody good with that? All right, so we're going to set up an interval. And it's got one place on it. I think we can do that, yeah? We need to pick values on either side. So what might you pick? Maybe a 0 and a 2. That sounds good to me. And you're going to evaluate this into what function? The derivative. So we need f prime of 0 and f prime of 2. So if you plug the derivative value, if you plug the 0 value into the derivative, what do you get? Positives or negatives? Positive. And if you plug in 2, what do you get? Negative. Okay, so this is a positive on my graph. This is a negative. Where is this graph increasing? Okay, from negative infinity, right? Increasing, negative infinity to L, 1. Good. And where is it decreasing? Yeah, 1 to infinity. Okay, so we haven't done anything different than we already did yet, right? Does this look okay? Yes? We're all good? Do you know what this graph looks like, right? What's this a graph of? It's a parabola opening down. So does it make sense that it's increasing first, decreasing second? Okay, good. All right, here's the first derivative test part. So technically, let me make sure. This is part A, finding the critical points. This is all part B, right? Finding all the increasing, decreasing stuff. Part C is to apply the first derivative test. So thinking about this picture over here on my graph, if the graph is increasing, I just want you to Put your arm in the air that shows me what the graph is doing. What's it look like? Okay, so it looks like this, right? Most of you are doing this except for Caleb, who's using the other hand to go like this. Yeah. Which is true. You got it. Yeah. So the graph's doing that, right? What happens for the other side? Show me. Very good. Now half of you are doing the other arm just for fun. I can tell. Looks like that, right? Graph's going up, graph's going down. Can you tell just by drawing those simple little line segments in there what's happening there? What's happening at 1? It's a relative or a local max. Yeah, absolutely. This right here is a max. So part C tells us that we have a maximum at x equal 1. Now, what if, say for instance, on Jupyter, or not Jupyter, I mean, on WebAssign, they want you to write it as an ordered pair. How would you find 1 what? Plug in 1 to the original equation, right? So if you plugged in the number 1 to the original equation here, what would you get? 5? I think that's right, yeah. So we might actually be requested to write this as the value 1, 5. I don't know what it's going to request you to do. I didn't actually go through to check that part of it, but that's how you would do it, okay? So this is a maximum value at x equal 1. Graph it. Make sure that it makes sense to you. Take a look at this graph. So if you were asked to do this on a test and it had this statement where it says use a graphing utility to confirm your results, you're just going to sketch a graph on your paper, okay? So you're going to sketch what graph your calculator is showing you. And what I have written down is that it looks something like this. There's 1, 5. Does your graph match something like that? Roughly speaking. Okay, well nobody's complaining, so it must be okay. At least I hope. Okay, so this is really just like 2 little pieces at the end that were a continuation of what we've already done, right? All right, let's try another one. Find the critical numbers. Find the increasing, decreasing, relative max min. But this one is a different kind of equation, right? It's not polynomial. So what do we get for our derivative on this one? One-third, then what? X to negative 2/3. Yeah, and so if we, and in the denominator, right? So this would be like, you're telling me cube root because of the 3 underneath the 1, underneath the negative 2, and then this would be x squared. Looks something like that. Is everybody okay with that change? And for critical numbers, we're supposed to set this equal to 0 or equals to does not exist. Right? So what do you find out? Yeah, it does not exist at 0. So this does not exist at x equals 0. How about setting it equal to 0? Doesn't work, right? It never equals 0. Agreed? The only way a fraction would equal 0 is if the numerator equals 0 and this numerator is 1. Yeah, so the denominator equals 0 is it does not exist location, but the numerator never equals 0. So we only have one possible value where it could be changing from increasing to decreasing. So there's one critical number possible. Okay, x equals 0. So we're going to create our number line with x equals 0 on it. And can we test either side of x equals 0 pretty easily? Sure. I like the numbers -1 and 1. Are you guys good with those? Okay, so where am I going to plug these numbers back in? The derivative, very good. So we're going to find f prime of -1 and f prime of 1. And what do we get? Signs are what we're looking for, right? Do we get positives or negatives? Yeah, and both of them are positive, aren't they? Yeah, because we actually are squaring whatever that value is underneath the cube root, which changes, doesn't matter the sign now, yeah? Okay, so these are both positive. So what can you tell me about this graph? Where is it increasing, decreasing? It's increasing from negative infinity to where? Well, yes, from a negative infinity to positive infinity, but we have to have a breaking point at 0, right? Yeah, so we have to do negative infinity to 0, and then 0 to infinity. I think we don't actually have an asymptote here. When you graph this, you'll check this out in a minute. Okay? It's an interesting graph. Okay? Got the increasing. It's never decreasing, right? Okay? What can you tell me? So this is part B. I didn't label it. All this work is part B. Part C talks about relative max-min. Well, the only possible place of a relative max-min is at 0. And what's happening at 0? There's no change in slopes on either side, right? It's positive on the left, positive on the right. It's kind of like the graph of y equal x cubed that I drew originally. So back on our screen where we had all of the first derivative test options, this is number 3. F of c has the same sign before and after 0, right? Same sign. So there is no local extrema, no relative extrema. Oops. So this is no extrema. So what's happening on this graph? What's it look like? Can you sketch it? Can you graph it and then sketch it? It's not quite right. Roughly like this. Something like that. The original graph. We're looking at the original graph. The original graph is increasing everywhere, right? Except for this one weird thing happening at x equals 0. Can you tell what's happening there? We haven't actually seen this happen until this graph, this whole semester. What would happen if you drew the tangent line there? It'd be vertical, right? And that was one of our places where we said that tangent lines wouldn't, not tangent lines, but derivatives wouldn't exist, right? Vertical tangent lines. This one has it. Has a vertical tangent line. Now, if you graph the derivative, what you'll actually see, if I remember right, is I think you're going to see a sharp turn on the derivative. That's not right. You'll see an asymptote on the derivative because of the way this is graphing, I believe. Yeah. But the original graph is what tells us whether it's increasing or decreasing. Okay, is everybody good with the picture? It confirms the details that we wrote down, right? Yeah. All right, last one. Basically the same instructions as before. It's just that they've got this extra sort of interval, 0 to 2 pi at the beginning. And the reason they do is because, again, it's a sine graph, right? We've got these infinite sort of going up and down business, so we've got to limit it. So we're going to start out with finding the intervals where it's increasing, decreasing, which means finding derivatives and set them equal to 0 and all that jazz. So what's the derivative of this function? Good, 1 plus 2 cosine x equals 0 would be our next step. So what is the cosine of x going to be equal to? Negative 1/2, your favorite. We just talked about this when we did it for positive 1/2. Where on the unit circle is the cosine value and negative 1/2 now? Okay, 4 pi over 6, like 2 pi over 3, you mean? 2 pi over 3? Okay. 2 pi over 3 works. Where else? I think you're looking at sine values, maybe, Hudson. Yeah.
How about 4 pi over 3?
4 pi over 3 is the other one, yes. The pi over 3 values are closer to the y-axis, which means the x values are smaller, and cosine values are the x values. So that's why it's going to be the pi over 3 values. Yeah. Okay. We have 2 values, and we're trapped between 0 and 2 pi. So let's get our interval set up. We start at 0. We have 2 pi over 3. We have 4 pi over 3. And we have 2 pi. And we need a value in between each of these. So let's pick some really quickly. We did 1 earlier. I think, let's see, I have written down 3 works here. And 5. You guys good with those? 3 should work.
Cancel on top of bottom.
Okay, is that good? All right, so we're going to plug those into the derivative, right? So we want f prime of 1, f prime of 3, and f prime of 5. All right, so what is f prime of 1? Positive or negative? Positive? How about f prime of 3? Negative. And f prime of 5? Positive. They don't always alternate, but a lot of the time they do. So we have positive, negative, positive. So where is the graph increasing? 0 to 2 pi over 3. And then where? Good. 4 pi over 3 to 2 pi. And where is it decreasing? Two pi over 3 to 4 pi over 3. Okay, so that's the increasing decrease. This is all part A. Part B is to confirm where we have a relative max or min. So back on my graph, increasing means going uphill, decreasing is down, increasing is up. What happens at 2 pi over 3? It's a max. There's a relative max at x equals 2 pi over 3. And what happens at 4 pi over 3? There's a min, right? At x equals 4 pi over 3. Right, can you guys see that from the picture? Here's my max. Here's my min. Graph it real quick and we're done for the day. You can make your graph go from 0 to 2 pi. Original equation, x plus 2 sine x. My graph looks something like this. Maybe not quite what you expected. This would be my 2 pi over 3. And this one is my 4 pi over 3. So do you see this is a really good example of it's not the biggest value on the whole interval, right? And this one is not the smallest value on the whole interval. But if you looked locally, right, it's the biggest value around that pink area there. And if you look locally over here, it's the smallest value in the blue area over here, right? Because our interval stopped at 2 pi.
2 pi minus 0.001, that's not higher than 2 pi over 3.
Hang on a second.